Hello, everyone, and welcome to Your Desk University, where we bring live learning with AEC tech experts directly to your desk. Today, we have a special episode because our speaker a few weeks ago had some problems with his internet connection. And so today, we're going to be learning about regular, machine learning, and homegrown. Let me see here. So what you're seeing on my left is Homegrown, a small machine learning algorithm tool that automatically places furniture inside of a room and a space based on its layout and the door location. You're going to have the opportunity to ask any questions that you have or I have for the developer of that. And with that, I will bring him on. Hi, Oliver. This is Oliver. He works at AHMM. He's the developer of Homegrown and Regular, recently released on Twitter, which you've probably seen. And we had you a couple of weeks ago, didn't we?
We did, and back then I worked for AHMM, and now I'm days away from starting at the new office. But they very kindly let me back in and logged me into everything, so all should be good and working, and I'm sort of ready to chat a bit about Homegrown, Regular, and just show you what I've been up to, really.
Yeah, I'm definitely fascinated to hear about it. And I see a couple of people tuning in. Go ahead and say hi down in the comments below. And we look forward to answering questions afterwards. And Oliver will have access to the stream to watch that as well. So with that, why don't we get started and talk a little bit first about Homegrown and what it does.
Cool, yeah, so Homegrown was being developed around this time last year, actually, it wrapped up. And it'd been coming together for a little while. I had a strong interest in machine learning. I completed a course there. My architectural firm designs a lot of apartments, hundreds every year. And I had an interest in sort of volumetric housing, panelized modular housing as well, that were all kind of coming together. And Homegrown was basically an attempt to take a look at bringing these interests together and saying, we design a ton of apartments. They're always kind of unique in very sort of small kind of finite ways, but also in terms of larger strategy, often there's a lot that can be shared between projects. And so I thought with Revit, so I'm on the digital design team of AHMM, or it was, and I'd be developing kind of custom softwares to help us kind of design in new ways to sort of automate some of the aspects of the way that we work and sort of generally try and win advantages for our workflows by seeing if I could standardize things using a code-based approach. Homegrown was kind of, I pitched it to the company and they sort of signed off on it and said, yep, sounds great. Okay, how long do you need and everything? So I kind of filled out all those details, sent them over and we said, good, all right, have a go at building this thing. And it had been sort of percolating in my head for a few months, really, even before I kind of got sign off exactly how I'd approach targeting this aspect and this problem and how we'd represent apartments and how we'd sort of rank apartments and everything like that. It was all kind of going through my head for months and months. So by the time it came to actually sitting down and writing code for 4 months, I was more or less just kind of raring to go and I just wanted to build it, test it, get it out there. And funnily enough, it kind of went largely to plan. So Homegrown is part of AHMM's sort of Revit ribbon, a custom in-house ribbon that sort of I've built full of tools for architects. And it is designed to make the process of apartment design sort of a little faster, smoother, more efficient, more standardized, and to be as usable a tool as possible. So here we've got this GIF, which is a pretty good demonstration of it. I've got this file kind of loaded up in the background as well. But it is essentially a 2-click tool for architects. They press a button to kind of kick it all off in Revit. And it's simply you click once in a space that is enclosed, and you click another time to roughly indicate where you want an entrance apartment entrance door to go. It looks to our database of apartments, ranks them, scores them, filters out the ones that kind of don't really match, and it will come back to you with anything that we've previously designed that is going to fit well in this space. And you can review from a bunch of options sorted from best fit to kind of least best fit. Click on the one you like if you like any of them. You can also sort and filter. There's things like the number of beds, the client, the year they were built, that kind of thing. Double click on the apartment that you like if you like any of them, and it's going to recreate that for you in situ, regardless of sort of any minor differences in shape or rotation or mirroring and handing, that kind of thing. Is that a good enough intro?
Yeah, that's a good intro. I do want to dig into it a little bit. If I can ask you some of these questions, because I think that people see things like this and they think like, wow, this thing is so impossibly, powerful and amazing. It designs the whole thing. That's what some people see. Other people see and they're like, oh, that thing's all just marketing magic. And so I kind of want to, if we can just dig a little bit into what you did and how you did it to kind of like, I don't know, kind of connect those two worlds and help people see that there is something happening and no, it's not, designing absolutely everything about the project. That would be, I think, really, really interesting.
Sure thing. Okay, so I have a paper I could sort of dive into, and I think we can go into any amount of detail that we like on this pretty much. So
Okay.
feel free to ask any questions that kind of come to mind. If anyone asks sort of in the comments as well, very, very welcome. But this paper was published in
And
October
we
as
do have
part
a
of the...
couple people watching live with us. So hi guys.
Welcome.
Way to be subscribers and see things that get streamed live as they happen. So welcome, definitely. We're excited that Your Desk has people who want to follow it like that. And we hope that we can answer your questions alongside everything else. So just so you know, Oliver, I'm showing right now your left side of the screen, kind of the PDF area. So we can
Perfect.
stick with that, and we can also do the full screen if we need to. I'll just switch back and forth.
PDF works great for now.
Perfect.
So we were looking to build a tool that was not quite fully generative and algorithmic. It wasn't kind of fully systematized either, and it wasn't also looking to kind of build something that is entirely unique every single time. It was sort of trying to find that sort of sweet spot between the two. So the very first thing you need to do when sort of dealing with machine learning is, of course, gathering data. And of course, this helps us understand, the sizes, the various kinds of apartments that we create, things like the shapes, just generally like bits about the data that we wanted to understand what it was that we were dealing with. So what I did is, and I can actually open this file up and spin around it if it's useful, Timon.
Yeah.
I created 80 something apartments. Let me just...
Can we go back to that GIF just for a second? Because I want to ask some of the questions I know you're going to get to, or yeah. So when we're looking at this, it's automatically placing all these pieces. And I know you're going to get to this, but I want to kind of give the short 20 or 30-second rendition, and then we can get into a little bit more detail. But how is it identifying the different apartments? Because obviously it's putting the beds in different places. So at the very, very highest level, kind of the 10-second version, and then let's dig a little bit deeper in a moment. But how does it decide which apartment to put when you put that door in there? What are the like 2 or 3 key features?
Okay, it uses, so we measure 11 features that we thought were useful for rating similarity between spaces. So fundamentally, we always want to take a look at this empty space that we're looking to put an apartment within and measure things about that. And then we have the same measurements for all of the apartments that we've saved. There's 89 apartments that we've saved, and we've had to do a lot of data standardization in order to make sure they're all talking the same language, they're all working to the same parameters, that kind of thing. And it effectively, on each of those 11 features, it calculates a similarity score. So in terms of, how wide they are, how deep they are, how well the shapes match, these kind of things, you calculate how similar they are in each of those 11 features. And you can, if you like, total them up and say, okay, across all those 11 features, it's dissimilar. That means it's this good a match. And for that apartment, across the 11 features, it's that similar. So for that apartment, it's that good a match. There is a mathematical formula in the paper, but
yeah,
short,
and let's definitely dig into that. And then when you're looking at like placing all these pieces, if someone was to do this same idea, same concept with another, something else, how do you kind of locate all those pieces of furniture in the space and then put them in a place that seems to make logical sense? Do you have like a little bit of magic here? I know you're willing to share because we've talked about this ahead of time, and we're really grateful you're willing to dig into this a little bit more.
Of course, very happy to really get into the weeds with this. So fundamentally, everything is located in relation to a reference grid, what we call a UV grid, which has an origin point at 0, 0 and has a far corner point at 1, 1. And sort of, if you can imagine kind of this grid, I have a good slightly blurry figure here. Is any point in space can be related to this 2D grid. And when you're recreating things in Revit using the API, you're largely either looking at lines for things like walls, which is really just 2 points, or you're looking at a single point. So if you're placing a chair, there's a single point in space, and we're talking about maybe it's 0.1, 0.3, or if it's in the very middle of the space, it will be 0.5, 0.5. So here, this little diagram shows an example of sort of taking a point in space for our apartment grid. So there was a whole question about how we lay this grid out and what is the best way to sort of box a grid around the department, even if it has an irregular shape, if it's rotated funny. So I can even take a step backwards and talk about that process, because it was something I had to sort of get a bit creative with. So very commonly what you would use for this approach is something called a minimum bounding box. So it's an algorithm that sort of tries to rotate and fit the smallest possible box and kind of shrink wrap a rectangle, if you like, around a shape. For this, though, we found that sometimes it was a little unintuitive how it would actually find the smallest box, and actually the smallest box wouldn't necessarily, its grid lines wouldn't relate to the geometry of the space very well. And we wanted ideally the geometry of the space we were looking at, in this case a Revit area, to directly inform the way the grid lines would fall. To do that, then I came up with a pretty rapid approach, which I call like dominant vector or most popular vector. And effectively what it does is if I've got like an L-shaped apartment here, is I can read the boundary edges of the space using Revit's API, and I can group them together by their orientation. Doesn't really matter where it's oriented, so it's it'll give a consistent output regardless of how you rotate that shape. And I group all those lines together and say, okay, longest line, that's the dominant vector. And so that becomes the basis for laying out my rectangular grid. And then simply the other grid line is going at 90 degrees to that. So in this example here, I've got a little L-shaped apartment here, and the dominant vector is the 0 degrees, which is the red, because that has the longest overall length of 24 meters. So that's how I'm going to start. And as you can see then, I'm able to use this as the basis for creating a rectilinear or rectangular grid around the shape. And the nice thing about that is, like I said, regardless of how much or how little you kind of rotate the actual apartment in question, it's going to lock that grid on consistently. And it works pretty happily for all different sizes and shapes of apartments. The other thing that's useful about this is simply just, I mean, the computer wouldn't mind, but I would mind sort of as a human trying to interpret the data, is when you lock on to the outer boundary shape of an apartment, is often that tends to have a really big impact on the logic of the internal layouts as well. So for an L-shaped apartment, you can imagine most
like
of the
having a
walls,
really long arm is really going to skew how things get laid out, is what you're saying. Like in that L, if you were to take the L and you had like a really long extension piece,
it's gonna really help lock on this kind of dominant vector grid that we put down. But if you can imagine, if there are to be walls inside this apartment, they're almost certainly going to be running sort of parallel and perpendicular to these grid lines we've placed. So the external shape tends to affect the internal layout logic. And that means when you're looking at your data, it's really, really clean, because your walls very often are, you know, locked in the V-axis and just going along the U-axis or vice versa. But it just means you're dealing with a lot closer to the inherent layout logic of a space. That might have been too wordsy. Sorry. No. The other thing is, so we lay down on a grid, and we always sort of take the, if you like, kind of the bottommost, rightmost grid corner point as sort of our anchor, which is useful for when we want to sort of understand, are we dealing with the apartment as it was originally laid out, or is Homegrown suggesting actually a flipped version of an apartment to you, and can even give you a little, you know, expandable icon to show you how the furniture would look laid out in the target space. So if I'm looking at an L-shaped space one way, but actually the original apartment was an L-shaped space totally differently, we can actually orient the little image that Homegrown shows you to correctly show it oriented to your target space. So it's always going to give you, if you like, the most appropriate image for your target space when it's recommending an apartment to you, which is good. It means you don't have to do kind of mental flipping in your head.
And I think I cut you off earlier, but I think you were going to show us kind of these original spaces, your original kind of database of spaces that you were kind of pulling off of.
Sure thing. Should we go full screen?
Let's go for it. Yeah, let me switch to a different screen here. You're up.
So while we do actually save apartment data to a Microsoft SQL server, it has to originate somewhere, and so it lives in a Revit file. I guess it's a good place to keep a lot of Revit information together. But fundamentally, what I did is I had to use an intermediate file and do a lot of kind of cutting and pasting of geometry into this intermediate file, tidy it all up, and then put it into a layout library. From there, I had to build some tools to look at standardizing, the bed types and the wall types and the everything types, so as to clean a database. These are all from live, real projects, and the teams maybe using different versions of the software, have different modeling approaches sometimes, different families, I had to really go through that and sort of with a fine-tooth comb and standardize that data so we can always guarantee the flat entrance door is always going to be one particular type for all of these 89 apartments. So we have these 89 apartments, and I switch back to the left here. What I then had to do is to save the information of all the internal elements in relation to this grid. So I want to understand where they sit in space on this UV grid, and I want to understand how they're oriented. So maybe take their rotation from the U-axis. I then, in order to maximize the utility of Homegrown, is I save 8 imprints per apartment. So I can zoom in on this, and we can sort of say that, this L-shaped apartment here, this maybe is originally how it's laid out, but I wanted Homegrown to be able to look at a space oriented like so or like so, and also recognize the same apartment would fit in there perfectly fine, just rotated and flipped and
or
whatnot.
rotated around.
This maximizes the utility of Homegrown, definitely. So each apartment is considered as thoroughly as it can be. And the nice thing about this is that so I have these 89 apartments. I multiply that by 8. I think that's 712 top of my head. It's about that much, 800. And Homegrown actually looks at each of the 800 apartments, and it filters them and it ranks them, and it sort of compares their sort of similarity scores across our 11 features. And the best thing is I don't have to put any logic to tell Homegrown which one is the best match. Through comparing those 11 similarity features, the best one is going to percolate to the top regardless. So
can we look at those similarity features? I know you can't share all the magic sauce inside of there, but I think you had a matrix that you were kind of showing. Yeah, this I think is kind of, that's the geometry matrix, right?
Yes. So this is how we compare shapes of the apartments. As initially, I was wondering whether I should create taxonomies for like L-shaped apartments, long rectangular apartments, square apartments, that kind of thing. But I was inspired, and there's a reference in the paper to an very old machine learning paper from the 50s, where the author looked at sort of recognizing handwritten digits, and he very much took this approach. Is you kind of take maybe what someone's handwritten and you kind of break it up into this grid, and you're able to effectively kind of compare a canonical 1 or a canonical 0 or 3 or whatever to what the user sketched. And if you look at it sort of grid point by grid point and run a comparison, you can overall see with a good amount of accuracy what that handwritten digit is actually likely to be. So in this
so you're
case,
not looking at like, is the length similar to the length, or is the width similar to the width, but is the kind of the layout shape similar in this UV system to an original kind of apartment in its own UV system?
This is one of the features, but you're actually right, length and width. In fact, by coincidence on page, we even say apartments whose area is not within 10% of the candidate space, or whose grid dimensions, so length and width, are not within 10% of the candidate space, as UV grid dimensions are disregarded. So that means we kind of we instantiate a hard filter. So if we're looking at in the 800 apartments, if anything is not within 10% of the area, the length and the width, we chuck it out immediately. We don't even need to consider it. The rest of them are kind of soft filters. So the hard filter just says go away. The soft filters take the remaining, I don't know, 100 or 50 apartments and generate scores. And the scores are what we use to actually best rank and match. And one of the features that kind of is in the score, and it's a pretty important feature, is the shape. So in order to look at the shape and compare the shapes, it's actually very rapid. We create, if you like, lists of lists. We break up according to our UV grid, our candidate area into 10 by 10 grid. And within each of those sort of grid squares, we do an analysis. And again, we just place 10 by 10 points within each square. So 10 by 10 by 10 by 10. I think it's 10,000 points in the end. And we go, okay, within this square, of the 100 points, we're looking at how many of them fall within the candidate area. And there's a very fast Revit API method, point.project, I think it was, to tell you whether a point lives within a face, is the Revit API term. So we can do this incredibly quickly. It takes milliseconds. And so we look in our nested list structure and say, okay, 100% of the points we place do fall within the area here. But if you look in the corner, only maybe 30% of them do. So I mean, I've represented this 0 to 1 score from black to white. But as you can see, you get a decent imprint. And this really is just a list of numbers. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 0.3, 0, 0, 0, 0, 0, probably about 0.5, 1, 1, 1, 1, as we go through the grid. Like I said, doing this is very quick. And then you already have that matrix information saved for the 800 apartments in your database. So that's very quick to access. And all you're doing is generating it from the candidate space. So when you've got a brand new space that you've never seen before, you're trying to put an apartment in, you generate this very rapidly from it. And then you can take the two matrices and subtract them from one another and take the absolute difference. So in this case, we're looking at 0.638, 0.781, and we subtract the two from one another. And what you can see is the similarity here is 0.5. It's actually pretty low in the end of the day. And as you can see, these two shapes are very dissimilar. They're nothing like each other. So that's not going to do too well in the old shapes department. But we take a look at things like where the entrance door is located in space, its angle. We take a look at the locations and lengths of external walls and internal walls, these kind of things. So there's these 11 features that we've not disclosed fully, but they're kind of half disclosed in the paper. For a feature like this, it's actually very easy to calculate the difference. You're just taking one nested list structure and another and subtracting them. For other features like the area, so as long as you're within 10% of the area, you're fine, we will consider you. But there is also a soft filter for, like this is a soft filter. There's a soft filter for things like the length, the width, and the area. So we want to go, okay, fine, you're within 10%, but how close are you? And this was a tricky statistical challenge because you're dealing with continuous numbers. So if I was to say, you're looking at an apartment, okay, let's do American, 600 square foot. That could be an apartment, couldn't it? Could it?
Or 400 square feet, sure, totally.
Okay.
I know you're probably used to working in square meters, aren't you?
Definitely. If I was to say, I'm looking at
by the way, is ResearchGate? I just found the paper on ResearchGate. Is that the best place for people to find this if I post the link?
Yes, I think they're working on a research page for AHMM's website, and this will eventually go on there. But ResearchGate is the perfect place to find it right now. And I've got some posts as well where I try and publicize it. But yeah, ResearchGate. It's called Introspective Apartment Design, and it's
I posted the direct link to it into the chat so they can find it there.
So for statistical questions, we want to go, okay, you've got a slightly large one-bed apartment, maybe that's 55 square meters, or I don't know what that is in feet, and your target space would also fit a slightly large one-bed apartment. So we're slightly above average here, and we want to go, okay, that's very similar. But if you were to look at a slightly small one-bed apartment and compare it to your target space, which is slightly large, then we want to go, actually, no, you're not similar at all. So what we had to do is I had to put my statistics hat on, which is quite common with machine learning, and say we're looking at.
I mean, that is machine learning, right? It's just statistics.
It's a huge chunk, huge. I learned a lot of machine learning from StatQuest on YouTube, which is a statistics channel. It's super fun. I recommend people check it out, but it's primarily statistical, and that's why it's so easy for him to go into the machine learning stuff that he does. Okay, so I've posed this question: how do we rank similarity across continuous featured variables like apartment square meterage? And the way we do it is we look in relation to a statistical distribution. So things like the average, what's your average one-bed apartment? How close are you to the mean? And we can see then, if I were to map this out, I've assumed what you call a Gaussian or a normal distribution of data, which is an okay assumption to make, but perhaps not necessarily the best for area, but it's actually fine in this case. And we can look at the mean and say, okay, the mean is 51.26 square meters for this kind of apartment, and normally within a normal distribution, pretty much all the data, 99.6%, falls within 3 standard deviations of the mean. I hope those numbers are correct. So then we can say, in relation to the mean, we can map out -3 standard deviations from the mean to +3 standard deviations and say, okay, that's my scale from 0 to 1. We can then take real life continuous valued data, so 48.71, 50.85, and go, okay, you're both a little smaller than the mean. One is a bit more than the other. And because we've mapped everything out now from 0 to 1 in this relationship, we can now, again, just take the absolute difference and say, your difference is 0.2. That means your similarity is 1 minus 0.2, because similarity is the obverse of the difference. So this was a way I had to do a lot of testing in Excel to make sure this actually made sense. But in the end, it's like, yep, this is a robust measure. I'm happy with it. So that was a bit of a head scratcher. But that means we can look at things like length in meters, width in meters, area in square meters, and say, okay, your target space would actually be a great fit for a slightly large one bed. Here are, or we can sort of boost up the score then of the slightly large one bed apartments. I hope this all made sense. There's a bit of a statistical masterclass there. And then finally, I have and this confuses me because I don't do a lot of maths, is the total similarity score formula. So in the end, all it's saying is we're looking at the weighted sum of the differences, divide them by the total number of weights, so you still get a number between 0 and 1, and then similarity is 1 minus the weighted sum of all the differences. Now I measure weights, and this is important. So I can now go into some of the actual like machine learning bit, if we like, if you're happy with that. I think for the moment it will remain an internal tool. It's not impossible. I know there's been conversations had here and there, but right now there aren't currently plans for it. However, I anticipate similar tools will be coming out that might be more open source in nature in the next year. And the paper, if you can dig into the details, does give a good amount away without giving everything away. If you've got any particular questions, feel free to kind of send me a direct message as well. I'm very happy to sort of write back to you or even just have a chat.
Yeah, I also kind of appreciate like this kind of a conversation, the candidness about it, because everyone's not going to be looking only at apartments and looking at how do you lay out apartments, but there's so many other problems that could be solved, and kind of thinking about things in a similar way that you did can help them solve other problems.
Apartments are nice because they're quite a small, discrete, self-contained little problem space. They're quite easy to hold in your head. But I mean, if you were to do this for offices, there are so many differences between office sizes and shapes and stuff. I imagine it might be harder to do for offices. Apartments are sort of one of those things where like common resolutions are quite well gelled now. They're sort of crystallized to a point where, you know, there's only so many ways we're going to lay out a 2-bed apartment or a 3-bed apartment, that we're close to sort of reaching an ideal platonic solution for that. That means we can get a lot of value out of saved apartments, but saved offices, for instance, or restaurants or stuff might be harder
totally
to take
different
this approach for.
And I have to say, and I agree with one of the comments that's come in, is like, I really appreciate how much you are sharing, even as an internal tool. And I encourage others who are developing internal tools who want to share some pieces about it, but understand that there's still some IP that's important for us to maintain and hold, that's a good way of talking about things sometimes.
It's something that AHMM's been really good at. So for several years now, I've been talking at various public forums. Autodesk University, I've got a few classes where I sort of share our code and our approaches over the years. So this isn't the first time we've done this. It's the first time we've published research, perhaps, on this kind of stuff. But they've always been very good about sort of trying to tread that fine line between not giving away everything and all the code, but giving away enough so that it can sort of help benefit the wider industry, get people interested.
So can we see it in action a little bit? And I think we should probably hit maybe 1 or 2 other points, especially I think we wanted to also talk about regular a little bit. So I'm going to go to your full screen now.
Okie dokes. I am going to load up our layout library. No, I'm in the layout library. That's silly. I'm going to open my homegrown testing file.
And
And
while
this
you're
is
doing
the,
that, right, this is the layout library that has all the different apartments in there that you've already kind of located, that you're comparing your features against them, and then you're picking the one that fits the most, and then taking the UV grid coordinates and putting the furniture in that UV coordinate system. And I'm assuming you're using the door partially to identify like the 0 point, or how does the door play into this? And I know I'm probably asking questions that are going to extend this, but this is the kind of stuff we want to know about.
the door entrance point is one of the features we're really interested in measuring. So, I mean, it's always going to be probably on the outer edge of your grid, but you can, because it's still a point, it still has a UV, 0.5, 0.5, or something like that. You can look at the entrance location that's saved in the 800 apartments and compare that to the entrance location that the user clicks on. So actually, it's a very simple subtraction exercise for that. In terms of
Gotcha.
how we lay out the grid.
I was assuming like that was like the closest point to that was the 0, 0, but you're actually saying like, hey, no, that's one of our features. Like, I don't know, we might weight it heavier or lighter. You don't have to tell us, but like that helps to kind of identify the room that's closest maybe to that one. But I know we also still want to see it in live, so I know I'm diverting you in two directions. It's
That's
my
okay.
greatest skill.
we anchor the grid to kind of the lower right, lower left point of the grid that we place always. I mean, you just kind of have to pick somewhere in the end of the day. But what I can do is I can possibly copy some of this geometry over, providing none of it is pinned. I think it's not. And we can do a bit of an experiment now. Got to remember my shortcuts. And I can take the same apartment and I can rotate it, let's give me a number, between 0 and 360.
240.
240, that's a nice, neat number.
I know, it was a really bad random.
Okie dokes. Humans aren't very good at random. So what I'm going to show you is, I'm using Homegrown.
Neither are computers, actually, right?
Yes, actually true. I think random is one of those impossible things. So what I've done is I've selected a space, and here it's telling me I've actually got a UV flipped apartment. So compared to the original apartment that we saved, or the original apartment as it was found in a project, we've actually taken that apartment and we've flipped it on the U-axis and the V-axis here. So originally the apartment wasn't actually like this. It was like an L shape in a different way. But I'm going to recreate that in situ, and maybe it will moan at me, and it'll take a second to connect to our database. But here we go. We've got that, and it's recreated. And what we've effectively done is we've taken the original apartment and its UV grid, and we've stretched the UV grid to match this target space. And then we've laid everything out still according to the same instructions, so the same UV coordinates. So sinks are something that I have a nightmare placing because they're hosted. However, if you like, the original apartment was slightly longer in this axis, which is why these are now crushed together a little bit, and it was slightly shorter in this axis, which is why there's now a little gaps have opened up between the kitchen cabinets. So in England, 600 millimeters is a very common dimension for your kitchen furniture and stuff. We don't want to change any of the critical dimensions. Instead, we want to sort of just let things float in space a bit, so that the critical dimensions are maintained for things like beds and access areas, these kind of things. So I've taken this apartment, I've recreated it. Now, our 240-degree place is, I'm going to do the same thing. I'm going to tell Homegrown, doesn't like me. We'll try again. I'm going to tell Homegrown, recreate the same apartment now, but at this really random rotation. And it shouldn't be UV flip now. I think it's going to be, here we go.
And so before you click on that, so what it's telling you right now is and I'm going to actually zoom in here. All right, I can't, let's see. Yeah, I'll pause on zooming in. So it's basically telling you like, hey, here are some apartments it might be. And then I think on the top right, if you can see that, it says like 95% match, 80% match to kind of like help people know.
Yes.
And I love this. I think this is our next area of development, I think, in AEC is this augmented design, where the humans still making the decisions, still helping to do things, but the computer's kind of like providing options. And we've seen that a lot, right? And this is cool.
It should hopefully scale as we create more apartments. But yeah, the idea is to very much to enhance the way architects work and not cut them out of the picture. It can, if you don't know what you're doing with Revit, it can take a while to create a decent door family or, create the kind of content you need. With Homegrown, we're able to standardize that across the business now, and everything will cut great and plan and section and look great at all these detail levels and zoom levels and stuff. The parameters will be like absolutely watertight. So it gives us control over sort of the content, the Revit content, and the data, which means you spend more time designing and adjusting and perfecting and less time battling the software or sort of trying to figure out how to do a fairly rudimentary task. The stuff that hopefully as architects we kind of trained to do, that design stuff. As you can see, we have the same apartment now, but I've rotated the thumbnail, and actually it says UV switched V flipped, which means now if you took the original apartment as it used to live, we've taken the UV axes, we've flipped them, so now they've actually swapped, and then we've flipped in V. This was kind of a nightmare to wrap my head around in the beginning, how to do all this, but it means we've got the best match apartment for the space. And again, it should recreate in situ, no problems, minus the sink. I told you the sinks are a nightmare. But if we go from our old apartment now to our new apartment at 240 degrees, everything still lives exactly kind of where it should be, minus little sink guy over here. Actually, maybe that's cool. Maybe that's the new trend.
That's how our sink is in our house. My wife hates it and she wants to get it changed, but it's at an angle like that. Maybe it's not sticking off the countertop, but that's kind of cool. And I like how you've shown like, hey, this is kind of where my development stopped. My development stopped at like placing things on a UV coordinate system. I think people can already see it and think like, ooh, I can see where this can go next. And I almost love that piece where you're like, ooh, I could see how you could stretch the sizes of the cabinets, or you could like move them closer to the wall, or whatever those like next pieces are that people are seeing. And it's because that's kind of what something like this developed is. It's right. It's like one idea and then one thing and then one thing, just kind of like little steps as we go. Um,
It
so
could be further, resolved. I mean, I've already have kind of brainstormed in my head how I might take these kitchens that are quite complex layouts and begin to resolve them and sort of help line up the cabinets, these kind of things. The nice thing about having control not only over the content but the data is it means you can unlock a ton of downstream workflows. So if a bed knows that it's a bed and it knows that it's in a particular bedroom of a particular apartment type, it can know, is it the right size bed? Have we got the right number of dining table chairs? Have we got the right number of sofa spaces? Is the corridor, now that it knows it's a corridor, is it wide enough? And you can begin to do, even like compliance and regulatory checking. I've built a suite of unit tests for all the apartments in our library in Python that just check, for instance, whether you've got the right number of dining table chairs, sofa spaces, the right furniture in every room. And that can check 89 apartments in a couple of seconds. So the more standardization you have over the data, the more you can unlock even more cool tools downstream.
yeah, cool. Anything else you want to hit on before? I know you want to talk about regular and we're running short on time here. So what are your thoughts?
I will briefly go into some of the more machine learning
All
because I
right.
said we have these 11 features and we
Mhm.
weight them. And the way that we weighted them is actually one of the cooler parts of this paper. I need to scroll up and find it. But what I did is we actually originally weighted all of our 11 features at 1. They were all completely ranked as if they were equally important, and we knew they wouldn't be, but we wanted to use machine learning to figure out those weights and reverse engineer them from data. So what I did is I had a bunch of architects recreate 160, I think, apartments using these equal weightings. So we weren't sure if Homegrown would be recommending the right apartments for the right spaces yet, and that was fine. We were open to failure. And then we had them recreate a bunch of apartments and a bunch of spaces, and then we gave them this kind of interesting UI, pop-up UI with sort of these sliders. And we wanted them to say, how well did Homegrown do? Therefore, we could know when certain features were prioritized, it would do a little better, and when certain features were like suppressed, it would do a little worse. Or we were able to reverse engineer when we did well from the sliders, if you like, what features were matching highly, and if we were doing well, then we're like, okay, boost those up. Alternatively, if the features appear to have no importance whatsoever on the score, we can then reverse engineer that and say, this feature doesn't really seem to matter. I used sliders because I wanted architects to think about design from a kind of gut feeling perspective. That tends to be how we design apartments. I didn't want them thinking numerically because you get some odd things when humans score things numerically, like 7 out of 10 is average, or 3.5 stars out of 5 stars is average somehow. And maybe it's because we're all very polite and nice.
I love it. Actually, a friend of mine just said this. He said he asks his wife sometimes, "Can you grade it on an academic scale?" Because it's like, "Oh,
Yes.
that's a 70. Oh, that's terrible. Oh, it's a 92. Oh, okay, so it's above average." And it's like 92. That's like near perfect.
100%. I think zero point 0.5 is a really harsh score, but actually I should be giving them out more often than not. So we were able to, I did have a look. We saved all this data to CSV every time someone ranked an apartment. We saved how well it did in each of the 11 features and then the overall total score. We could then feed this to a Python library. I think it was scikit-learn, and I used 2 different approaches just to double check, really. So I could have used one approach, but I wanted to be sure that, 2 approaches didn't come out with drastically different numbers, and they didn't. Used random forest regression and gradient boosting regression, so 2 regression techniques. And I even showed the weighting scores for both in the end. So this little graph, this bar chart shows the weightings that it arrived to. And as you can see, feature 11 and feature 6 are really strong. Things to do with the shape of the apartment appeared to matter a lot when it came to recommending the right apartments for a space. But of course, I can't tell you the exact features. I also messed up the labels here, so I'm really sorry if anyone looks at this paper and is sort of raising an eyebrow. These labels do not match, but the numbers do match. So sorry about that. I also have given little graphs to show that as we trained on larger and larger sizes of apartments, the numbers began to sort of settle. So you need more and more and more data to sort of train these things, and there reaches a point where you have enough data that the numbers begin to kind of converge and they don't actually jump around so much. But as you can see in the earlier iterations, the numbers are jumping everywhere. 20 apartments, they're here. 40 apartments, they're here. 60 apartments, they're here. They're all looking very different, these snapshots. But by the end, with 160 apartments, these numbers are actually super, super close. So we kind of
And that's
somewhat
160 flipped, so it's 320, and then all mirrored, so it's 640. Is that kind of how you?
that's the number of ratings. So the number of sliders
Oh, ratings, gotcha.
people kind of gave, and as basically as they gave direction to the algorithm, the more direction they were able to give. 160 apartments in, we were like, these numbers aren't moving around too much anymore. We're happy with these weightings. They're pretty good. And they were the same weightings that largely we would give as professional architects. So we were pretty happy. They made a lot of sense to us as professionals. I spoke a little bit earlier about the benefits of data standardization. I thought that might be a good segue into regular.
All right, that sounds good. And we have probably about 5 or 10, oh, we have probably 10 or 15 minutes to talk about that.
Okay, so we're going to go in a slightly different direction now, because I build a lot of tools to help architects with the day-to-day work. Homegrown was about helping architects kind of get on with being able to design and not spend so much time, rebuilding the same old things we might rebuild for all sorts of apartments in Revit. Regular is very much in the same vein. So as an architect who can code, I've had to build a lot of tools to help standardize data, to validate data, things like sheet numbers or fire codes or acoustic reduction codes or, COBie spec, all sorts of things where you want your data to fall into line to follow the same rules. And if you can't code this, it's tricky. If you've got 10,000 sheet numbers in your model, you've got 10,000 sheets in your model, and someone says, hey, we've got to change our sheet numbering standard from BS 1192 to ISO 19650. How are you meant to, without being able to code, check 10,000 sheet numbers?
Which actually, sheet numbers, I think, just rolled out with Revit 2022.
So
like sheet numbering kind of algorithms. By the way, if you're watching this and you've appreciated what Oliver's been sharing, hit that like button. It doesn't really help Your Desk University. It does highlight this particular episode for people to find across YouTube. So I would definitely ask that you help in that way. And yeah, back to the sheet numbering. I think it's interesting sometimes we as developers will kind of like help something along because we need it, and then it might become part of the primary software. And I'm not saying that what has happened is fully taken over what you've done, but why don't we look through some of the things that you've done with regular, because I think it's fascinating how you kind of like wrote algorithms to manipulate parameters and then you check them, right? That's kind of your key thing, is you're like maintaining that across the life of the project.
Yes. So what they've done in Revit is amazing, and I think it's long overdue. We've been using things like Xrev for that previously in the past, but it's all sorts of data standards for parameter values, numbers, names. And what I think Revit does is it sort of jams a bunch of parameters together and output that as your PDF name. This is more about validating it, especially according to standards. And the best part is you define the standards in plain English, and they can be anything you want. They can be as project specific as you want them to be. And we wanted to basically give you the ability to create rules for these data standards in your model. They're saved in your model. Everyone can access them. They're editable. They're really easy to edit. They're very easy to verify that your standard is what you want it to be, and then even share them around. So there is.
And this is open source. People were asking for open source. You did release the entire tool, all the code and everything. Is that right?
100% open source. It is up there on GitHub right now. My GitHub is Oliver E. Green. And then if you can find me on Twitter, again, I've got links to this. And the project is called Regular. So what I've done is I've released the first tool of Regular. It's the first one I've built. There are more to come. And it's meant to be a whole suite for sort of data creation, data rule creation, rule sharing, import and exporting, and data correction as well. So I've got a big manifesto about the big idea that talks about sort of some things that are tricky right now, because we don't have a lot of data standards that are very common within construction.
And between offices.
Absolutely. Agreeing on optimal data formats is hard. Opinions are strong and will differ. And very often my company, your company, X person's company have already built tools and programs to help with their own internal standards. And what we need is more shared standards. So one of the reasons software is so successful is, the XML standard hasn't really changed in probably since I was born. HTML, CSS, JavaScript, they kind of grow out, but like fundamentally the core remains the same and they have to. And therefore all the programmers can rely on, JavaScript working here 10 years ago and here today and probably work pretty much the same. We would benefit from such standards. So agreeing on optimal data formats is hard. So I've given you the ability to define data formats for your project, your company, your industry, whatever you like. Validating data in line with any format specifications is very hard. This is an automatic tool to help you do that. And finally, it's very costly sometimes to change standards. If someone decides we're going all underscore and we're getting rid of all the dashes and all the dots in our sheet number or our fire code or our specification code, that's a lot of hard work for someone who doesn't know how to code. So I built a tool it's especially really targeting BIM managers, construction data managers, all of you out there who've fallen into this role. I've also specifically highlighted, and I hope this offends no one, is many people who are dealing with BIM data didn't originally train as data managers. They might have retrained, but they originally trained as architects, engineers, project managers, what have you. And it can wind up being something someone winds up doing
and
in
for
their
developers
role.
who are trying to learn regular expressions, can they use this to kind of understand regular expressions a little bit better as well?
They can, yeah. When you export the rules, you can read the regular expressions in their sort of true format. However, regular creates slightly hideous regular expressions, and I can sort of give a demo of this. But basically, you create them piecemeal. You create them piece by piece in little chunks, and behind the scenes, that's translated to regular expressions. However, it's not as elegant a regex as it would be if you were kind of writing them yourselves. I can point you towards tools that are great for creating regular expressions and learning how to do them, but this is more about you don't need to learn how to code. You don't need to do anything. You just need to know what your data standard should be. So I've got a little GIF here. We had some issues. I'm on a new PC here, so we had some issues actually installing it because I'm not an admin. But this gives you a little demo of using regular. You've saved a bunch of rules in your rule manager, and you can basically just press fire and validate them, and it's going to validate our sound insulation rule across all 89 different things. These are doors, these are walls, these are windows, and I'm saying execute this rule. It validates it according to the rule that you've built, and I can show you how you'd build a rule because we have a whole examples page on our GitHub, which has got not just textual examples you can expand, but also there's a video example here on YouTube. So you can actually, there you go, brand new computer. I can't open YouTube, but you can actually.
And I did post the GitHub in the chat here so people can see it.
So we create rules using plain old English, pretty much. You decide which categories and which parameter your rule is going to track, and then you can basically add rule parts. And I've added a bunch of rule parts here for my pretend door code. It says, give me either ID or ED, a full stop, and 3 digits. And you basically, from the drop down, you select your chunks of rules, you add them together, and it will appear in sequence and create a rule. And in the bottom here, down by 0.09, we've actually got a little random example generator you can click, and it will generate infinite random examples that are compliant with the rule that you're creating. So you kind of know that it's right. So here I've used an option set to tell it we're looking at either ID or ED. I've created this option set here, and I've validated my doors, and you can see it's telling me whether they're valid or they're invalid. Where they're invalid, it's going to create a new randomly generated example again, and you can sort by all of these kind of columns, and you can actually edit the values in line, which is useful. So you can actually, my little GIF there, actually, if I go back, shows that where I've got sound insulation codes, I've intentionally built a few into the file that are actually wrong and they're invalid. And I can double click, I can change them to make them valid with my format, and they will update in the model. And it works for, fingers crossed, type parameters as well as instance parameters as well. So you can export this report.
So if your
to
team is like
CSV
making
format.
these changes, it will flag them or it will kind of keep them updated as you go.
It's correct at the moment of execution. So when you execute, it'll tell you whether they're valid or invalid kind of in the moment. And then if you were to correct something, it'll actually change it in the model for you. So if I'm correcting these values, these sound insulation codes, it'll actually correct that in the model for me. And then next time I synchronize, everyone has those changes. The rules are saved again, so they're saved into the model, so everyone has access to the same set of rules in the model. Everyone can edit them, providing you have regular installed. If you don't have regular installed and you're that one team member who doesn't have it, it's fine. The rules still live in the model. You just can't see them or access them. But yeah, these live in the model. The other thing about where they live, and this is part of regular that I hope helps the industry a little bit, is it's really easy to take your rules and export them. So there's an export rules
And where do they
button.
live? Where are they being stored in the memory of Revit?
Revit has an API called Extensible Storage. So we serialize everything to JSON, and we save them to a little regular part of the Revit file's memory.
If you didn't know this, any Revit file, you can 7-zip it open and find all the little files attached inside of there. So for all those who are learning, this is definitely a little trick. I wanted to go 2 places with you, Oliver. We've got about 3 or 4 more minutes. But as a developer, I wanted to talk a little bit about, you have these beautiful UIs you've built that are helping people. I'm assuming you're using WPF. If so, or if not, can you give maybe a couple things that you would recommend people as they're delving into WPF? And then second, I figure people who've watched us to this point, they're really committed to Your Desk University. And I want to share with them the announcement you made to me about your career change.
Yes, I've had the last 3 weeks sort of in total leisure, which has been amazing. Waking up late, cooking, it's been amazing. But yeah, I will be starting work on the 19th of April, which is, next Monday. And I suppose I'll say that bit kind of up front first, then I'll talk about XAML. I'm joining, I say, some of the UK's most incredible AEC software developers. It's a firm. It's founded by
Drum roll.
two architects, and I think they're putting out software and tools that are open source and they're free and they're amazing, and they blow my mind every time I see them. So I feel incredibly lucky to be joining their team. I'll be dealing in more of kind of a product specialist role for the minute, so dealing with UX, user experience and all that. I'll be joining Speckle Systems.
Speckle gets another great developer.
Who are
We love
Your
Speckle.
Desk.
They've been on Your Desk University, and we love the team there. So that's awesome.
They're over our side of the pond, and I've seen Dimitri and I've seen Matteo around London at various kind of events and stuff. We're all in the same kind of circles. So I feel really lucky to be joining the team and to get to work with them. And yeah, I hope to bring more Speckle into people's lives. I'm
And
really
Izzy,
excited.
and I don't know how big that team is, but that's wonderful.
I will be number 7.
And I have to say, like, just pausing from that for a moment, you're leaving AHMM, and you have such a great relationship with them. They invited you back to be able to show, like, what we did just now. and that is an AHMM product, and you're in their office getting reset up onto their infrastructure. Like, what kind of an awesome relationship is that? I have to say, guys, if you leave your companies and go to another company, not that I'm for or against that, but do it in a way like Oliver did, where he spent a lot of time setting things up, really documenting things, because he's leaving with such a great relationship. And I did that too a year or so ago, and I think that's really great. And Speckle's going to be really happy to have you, and the chat appreciates that as well. So thanks for sharing that, and thanks for being here at the end of the show. I still want to get to a little bit about the WPF pieces before we sum off. But if there are any other questions in the chat, I'm watching that. I just want to quickly browse here. I asked the chat, what's your hypothesis of the most important features in Homegrown, and didn't get any responses to that one, so no guesses. And I'm not asking you because I don't want to, infringe on that.
I've probably casually mentioned 80% of them even on this call. So
go back and rewind, fast forward. Oh, you're getting lots of hand clapping from the chat. So we love when you guys get engaged with us. It reminds us that we're not just talking to a camera. So thanks for that. And so, did you want to say anything more on that?
AHMM have been amazing, and I've had a lot of help from their amazing IT team to get set up so quickly today to plug back in and have nearly everything working. I wanted regular to work, but unfortunately I've got a GitHub and I've got GIFs and everything. In terms of XAML and WPF, then I learned there is an incredibly detailed series of courses on LinkedIn Learning, which used to be Linda, which was very, very good. And I forget the chap's name, American chap, but that doesn't narrow it down. But he had whole courses about binding, whole courses about sort of dependency properties and all that. I would recommend learning the MVVM architecture, model view model, which is what WPF was sort of designed to work with. And that encourages a really nice separation of concerns. And I think once your project gets big enough, you begin to appreciate that structuring, that very clean structuring between the different sort of aspects. Regular was actually my chance to learn MVVM myself, kind of properly, to build proper view models, to get proper binding, to learn about things like iCommand and iNotify property changed. It can be a little hard to learn at first. So, I mean, if people are sort of struggling, they can feel free to sort of reach out to me and I can try and help. I'm still learning about things like dependency objects and dependency properties. It is a big old framework. It's robust. Sometimes you've got to do some hacks to make things work all right, but it is hackable as well. So anything I've learned, I'm extremely happy to share with others. That having been said, if there are any WPF gurus out there who've been using this for 10 years, I would love if someone made a pull request and cleaned up my terrible XAML in regular, because it's not the best as clean as it could be. And that's one of the reasons I wanted to put this out in open source is to kind of partly learn from others as well.
Yeah, I've learned a lot from things that are on GitHub. I know WP. I just started learning a little bit about data binding, and I'm finding it to be so helpful when you're working with WPF. I'm doing Iron Python on data binding, so that's like a whole nother mess of language translation and stuff. But I'm glad I have been able to do that. So thanks, Oliver. Thank you everyone for your time, and who knows? Oliver might be one of our only third time on Your Desk University if you come back with Speckle at some point. But with that, I just want to appreciate everyone. Thanks for your time. I know this is crazy to be doing a off scheduled time, but you're getting thanks for sharing all your stuff and all your tools in the chat. And I definitely want to say, Oliver, thank you for that openness, and thank you AHMM for being interested in sharing in this capacity. That's pretty awesome.
Thanks so much for having me. Thanks everyone for tuning in. It's nice to have you. And till next time.
Till next time.